Assalamu alaikum students. Welcome to our first online lab session for the course Digital Logic Design. This is the lab for BCS 3A and I am Ali Roman. In our first lab session, we will be having the introduction to the Model Sim. The Model Sim software is basically a simulation software that is used to simulate our designs, our digital designs. So in this lab session, we will get familiar with this software, its primary interface, and how we're going to describe our design using this set software. In this lab session, also we will also be discussing the platform that is used to describe our digital design, and we will be using Verilog HDL that is used to describe our digital designs. This is basically the starter session in which we will be having introduction to the model sim as well as with the Verilog HDL. So let us first see the contents which we are covering in this lab session. So we will be having the introduction to this lab, and we will see how we're gonna download this software. This is a software that has been designed by the Mental Graphics. So what are the procedure which we will be adopting in order to download the particular software? So we will be using Model Sim PE Student Edition. So after the setup of this required software, we will be having the demonstration that how we're going to implement our designs by using the set softwares, and how we're going to simulate our design by using Model Sim Student Edition. As far as the reference ratings and acknowledgements are concerned, we are basically following chapter number 3 of the digital design with introduction to Verilog HTL. So we will be having the examples from chapter number 3 that are being described in chapter number 3 using Verilog HTL in order to implement our designs. So how to download the software? Basically, this is a student edition. Basically, we have to visit the Mentor Graphics website, and the link is provided in the slide. So we have to visit um, this website in order to download the software. So once you visit this website, you are required to fill this form. You have to provide this information in order to download the setup file. So once the setup file is downloaded, you have to run that setup file and install the software. After successful installation of the software, you are required to put a license request by placing a license request form. After successful installation, you are directly moved to a browser where you have to put the request. Once you fill the form, the license file is mailed to you on your provided email address. You just have to copy that license file in your installation folder, and for detailed instructions, please visit the given link. This is the link. This is the link. Basically, you have to visit that link, and the detailed instructions are also there, how to install the software and how to complete the license request form, and important information about your installation. So just go through this set of information in order to install the software on your desired system. So let us start our demonstration of the software, how we're going to use this software after successful installation. We just have to run the software. This is Model Sim PE Student Edition. We have to run this software. So this is the primary interface of the software. There is some sort of information that is for the beginners. If you want to, if you are using first time the particular software, just go through these instructions in order to get familiar with the software. I'm just skipping these and just going to the primary interface. So this is the primary interface for the Model Sim PE Student Edition 10.4a software. These are the set of libraries that we're going to use basically in order to describe our design. This is the command window in which we can enter some commands if we have to enter some commands and run some commands, and also to see if there are some sort of compilation errors or some sort of messages while working on the digital design. So first of all we have to do is we have to make a project here. So what we have to do is we have to go in a file menu, new, and then we'll select the option project. So we have to specify the project name. For example, this is our first lab, so this is DLD Lab 1. Where to save the project, the location of the project. So we have to make a folder, a new folder. I'm making a folder in C drive. Make a new folder and naming it as DLD Lab 1. Select this folder and set OK. We will be working in our default library name, that is work. All our compilation process and all our execution that has been performed in that particular folder, and we'll press OK. Now we have created a project that is being named DLD Lab 1. The next thing is to add items to the project. Basically we have to create a Verilog file here. Verilog file, basically that has been created by this step. We can either use this step or we can use the file menu to add the files. So basically we are creating a new file, so I'm picking up the option create new file. We have to name that file, and the important convention which we used to follow is that name the file the same way as which you will name your module name. So basically we have to design modules in that Verilog file in order to describe our design. We will be discussing that stuff later, how to design the modules and how we're going to describe our design by using gate level modeling. So we have to give the name. For example, I am giving the name as gate RDL. Basically I'm gonna simulate some gates, some combinational logical gates, and we're gonna set the file type as Verilog and set OK. Now if you see the hierarchy in your project, a file is being added with the name gate RTL.p. Verilog file extension files have the extension .p. So we're going to double click on that file. So an editor is being opened, and in this editor we're going to describe our design. So what we are going to do is just going through your first lab manual that is being provided to you, in which a basic example is been set for you in order to implement the design. This is basically figure 3.49 of your book. Basic combinational design with combination of AND gate, OR gate and NOT gate is provided to you. So we're going to describe that design. So basically what that design is, that we have an AND gate that is been connected with our inputs A and B. Then we've got OR gate. The output of AND gate is connected to the input of OR gate. Then we've got a NOT gate. And the output of NOT gate is connected to the input of OR gate. And we've got a third input C that has been connected to the input of NOT gate. So basically we've got three inputs of the system, A, B and C, and we've got two outputs that are basically D and E. And I am labeling this gate as G1. This is my gate number 1. This is my gate number 2, for example. And this is my gate number 3. And this is a wire that is connecting the output of G1 to the input of G3. What we are doing while we are performing our experiments on the breadboard while collecting the ICs, we used to connect the output of one gate to the input of other gate by using wires. So the same concept is been applied here. So basically we have a setup that has three inputs, A, B and C, and we've got two outputs that are D and E. These are our two outputs, and we have named our design as gate RDL. And this is the internal description of the design. So how we're going to implement this design on model sim by using Verilog HDL. We have to describe our module. We have to describe our module, and module is basically the name. You can say the name of the IC or the name of the project or the name of the design that you are describing basically. So that starts with the keyword module. Then we'll specify the name of the module, and we are saying it as gate RTL, and then in brackets we have to specify the port list. Port list are basically the interconnections through which we have to communicate with our design. So these you can assume as these are the physical pins that are used to communicate with our internal design. So the labels are A, B, C, and the outputs were D and E by semicolon at the end of the modular description. And we're gonna end this module with a keyword end module. So basically we have to describe our design in that particular area, end module and end module keyword. and one thing you have to note that we don't place a semicolon at the end of while we are writing the end module keyword. The next thing is we have to tell our design what are the inputs and what are the outputs from the specified port list. So we use our keyword output to specify the design outputs. So D and E were our design outputs, semicolon, and the inputs were input with the keyword input, input A, comma B, comma C. Since these are the scalar quantities, we don't have to specify the size here, but if in any case we have to specify the vector quantity or bus quantity, then we also have to mention the sizes here. We are going to see how to mention the sizes in our later examples. So in this step we have described our inputs and outputs of the design, and the next thing is if there are some wires that are the intermediate connections in order to connect uh, the two or more gates, then we have to define the wires also. So we'll use the keyword wire. So we were using one wire that was W1 semicolon. Now we have to describe our design. So our design consists of AND gate, OR gate and NOT gate. So we have to use the gate primitives. So we are using basically the gate level modeling, in which we are using the gate primitives in order to describe our design. We can describe our design in 4 different modeling techniques by using Verilog HDL. Either we are using the switch level modeling or the basic modeling, and then we are using the gate level modeling, then data flow modeling and the behavioral modeling. So we are basically working on a gate level modeling here in order to describe our design. So basically we are using gate primitives here. So the order of the gate primitives used in a design is not important. The most important thing is how to implement our design and how to achieve the functionality. So basically the design process is not sequential, that we have to design the AND gate first, then OR gate and then NOT gate, starting from input and output. We can describe our design from any particular module, any particular component in our design, because all our components in our design basically run concurrently. There is not a sequential flow in digital design by describing the gate level modeling. We can achieve the sequential flow design by behavioral modeling. We will see that when we are discussing the sequential logic in later labs. So I am describing our design modules component. So with the keyword AND, the AND keyword is used to specify the AND operation. Then the name of that, the instance name, the gate name, that was basically G1 in our previous description, in order to uniquely identify the gates when we are performing simulation. These names are basically the optional terms, but it is recommended to use those names. So first of all we have to specify the output. The output was coming on a wire and the inputs were A and B, and then a semicolon. Then I'm using the keyword NOT. That was basically my second gate, and its output is connected with E while input was connected to C. And the third is the OR primitive, and the gate was G3. Output was D and inputs were W1 and E and semicolon. So our description is complete. We have to save our file. The next thing is we have to compile our file to see if there exists some syntax or logical errors. So we have to right click on our file that is been in our project hierarchy, go to the compile option, and we can use a variety of compile options here. I am using compile selected. See here we got two errors. How we're gonna see what are the errors? We have to click on this red line, and these errors are appeared here. So this is basically the unexpected end of our source code basically. So basically we are using the keyword end module that is not being picked up. So there is a typo error EMD. So we have to correct this error with end module. Now if you observe that the keyword is turned red, so all the keywords are basically uh, in a different color from your regular text. So this is the way how we're gonna identify our errors. We're gonna close that, we're gonna save our file, and then we're gonna compile our file again. Now the compilation is successful. So this was the first step in which we've seen how to compile our design, how to implement our design in Verilog HCL. Basically we have to design our modules and we have to describe our designs in these particular modules. Till now we have described our design. So this is the first step in order to describe our designs. So the next step is to simulate our designs. Now to simulate our design, we have to design a test bench. A test bench is basically a driver circuit in order to design our in order to test the functionality of our designs, of our described designs. So what we have to do is we have to add a new file. We can also add a file from the file menu, or we can also add a file by right clicking here and the project hierarchy and add to file a new file. So the name of the file is gate RTL, and in order to differentiate with from our design, I am labeling it as T. This is a test bench, so T underscore gate RTL. You can have any unique name in order to describe your test bench, and the file type is Verilog. So this is basically a test driver file. So test bench are basically the design are the files that are used to test the functionality of our designs, and these are the modules that don't have any sort of interface. So basically these test drivers will gonna use the interfaces of your main design. So how we're gonna implement our test bench? We have to describe a module with the name, and that module don't have any sort of port, so we don't specify any ports here, and with the keyword and module. Then the next thing is what we have to do is we have to define our registered inputs. So we'll use the keyword reg A, B, C. These were the inputs that are being connected with the design inputs that are A, B, and C. So the easy way is whatsoever the inputs you have described in the gate RTL with the keyword input, instead of the keyword input, place it reg in your test bench. And the second thing what we have to do is describe our outputs for our test bench. So we will gonna use the keyword wire D and E. An easy way to remember this, what we have to do is uh, we have to define wires in our test bench, all those outputs that are being defined as an output in our main module. So D and E are described here as an output, so we have to describe D and E as a wire here, because outputs are basically coming through a wire and inputs are registered. So we have to define our inputs with the keyword bridge, and we have to define our outputs with the keyword wire. Then we have to call our module, or we have to instantiate our module. So the same concept which we are using in C++, in order to call a function you have to call the function with a function name. So same concept we are going to apply here. So basically here we are using the term instantiation, that is basically the process of instantiating or calling our module that is being tested in our test driver. So the name of our module was, if you remember, that was gate RTL, and that has an instance name. For example, if you are using the same module for multiple times in order to describe your design, then each of your separate instantiation should have a unique name in order to identify that when we are simulating our design. So we have to have a unique name. For example, I'm saying it as instance number 1. That is also optional, you can skip that, but it's recommended to use that. And then we have to provide the list of the inputs and outputs interconnected at the same placement. We can instantiate our module by order, or we can instantiate our module by name. So I'm using the instantiation of our module by order. So we have to use the same order which we are use the order to describe our design. For example, A, B, C, and D and E. So we will be using the same order here: A, comma B, comma C, comma D, comma E, and semicolon. The next thing is to provide the input combinations to set the value of A, B, and C in order to test the functionality of our design. So how to specify the input combinations? We have to use an initial block with the keyword initial. This is a case sensitive platform, so we have to be very careful in order to identify the keywords. Then begin and end. It's just like the brackets which we were using in C++ in order to specify some specific block. So here we have to specify the combination. For example, I'm saying A should be equal to 1 tick B 0 semicolon, or you can say that B should be equal to 1 tick B 0, then semicolon, and C should be equal to 1 tick B 0 and semicolon. Now what is this 1 tick B0 or this term? The first term, that digit is basically the size of the input. Since the A is a scalar quantity, is a single bit, so here we place 1. Then it's this comma here, that's in the syntax, and then next is the data type, or you can say that the numbering system in which we are giving the input basically. So it's B for the binary, so we are applying the binary input, and the last thing is the value of that input. So A is equal to binary 0, B is also equal to 0, and C is also equal to 0. So whenever the simulation starts, A and B and C, all the three inputs are set to 0. Then after some time we have to provide some delay element. For example, how to specify the delay? We are using software delay. Delays are specified with the keyword hash 100. Hash 100 means that we are producing a delay of 100 time frame, whatsoever the time frame of the simulation is. The next input are provided after 100 time frames, passage of 100 time frames, and now the next inputs are I am saying it as 1 1 and 1. Basically I am checking these two combinations A, B and C when all are 0 0 0 and A, B and C when all are 1 1 1. We can have the maximum number of combinations 8 here for the 3 inputs. So you can test all the 8 combinations here in this test bench. And the next thing is to specify the simulation time. You can specify the simulation time or you can skip that. So if you have to specify the simulation time, you can say initial. We have to use another initial block. For how much time the simulation should run, I'm saying that for 400 time frames, and after that it should get finish and semicolon. But I am commenting this term because I want to run the simulation once ever the program is in the execution phase. So this is our description. You can use this simulation time in your simulations in your description while in your test bench in order to specify for how much time your simulation should run. So we have to save this file, and the same process we have to compile this file. And let us see what are the errors which were made in this. Setup. See here, while describing our module, we have skipped a semicolon here. So I'm placing a semicolon here. So that was the error. Now I'm gonna again save this file. The errors that are being generated in these modules are just for your information, that how you're gonna see the errors and how you're gonna rectify these errors. Now I'm gonna compile these files also again. So there exists another error. No, our compilation is successful here. If you see this status that is been labeled as tick mark for the both of the files. Now the next thing is to simulate our design. What we have to do is we have to go to the simulate option, and we're going to start our simulation. Basically we have to start our simulation in our work directory. So we have to select our work directory, and we have to select our test bench module, that is t_gate RTL, and the resolution of the time frame we're going to use the default. We can change that into nanosecond, picosecond or femtosecond, whatsoever the simulation resolution you want to set. So I am basically going with the option of default, and we'll press OK. Now if you see these options here, these are the objects that are been appearing in your design module, and these are the instance name that is basically appearing in your test bench, as well as the module that is being tested here. So what we have to do is we have to right click on it in order to generate the timing diagram, and we have to add whatsoever that is provided in that description to the waveform in order to see the timing diagram of our simulation. So this is basically our waveform that is being shown here. And the next thing is we have to run our simulations. We can either run our simulations from this menu, this particular menu, if you say, where the time frame is being set to the 100 nanoseconds, and this is the icon or the cursor which is used to run our simulations, and we're going to press that and see the timing waveform are being generated. So if you observe that the inputs here that are 0 0 and 0, and the status of the output D and E is basically 1 1. So after 100 nanoseconds, this is 100 nanoseconds, the input are set to 1 1 and 1, and the outputs of D is 1 and E is 0. So this is the way how which we will be using in order to describe our designs and in order to simulate our designs. So I'm gonna end the simulation here, stop it, or end your simulation here. And this is all for today, students. I hope so you will be able to describe your designs right now. So since you are the computer science students, it would be easier for you to describe your designs because you have the extensive experience of C, C++ or the cloud programming platform. So basically the syntax of the Verilog HDL is similar to C. So it would be easier for you to understand and implement those modules. So this is all for today's lab. So in the today's lab session and also the session that has been designed on the Thursday, we will be practicing on this tool in order to describe our basic designs to get familiarity with the tool. And in our labs we will be using this tool, and we will be describing our design by using the set tool and simulating our design to see the functionality of our design.